So, in the last lecture, we were discussing about practical Kohn-Sham theory, and we have shown that the main problem in the Kohn-Sham framework is that you cannot write the kinetic energy term just in terms of density, you need to write in terms of one particle reduced density matrix. So, to write it in terms of density, you have to bring back the orbital picture, whatever is missing in the case of kinetic energy, where you write the kinetic energy of as a non-interacting system. So, rest of the term you push into the exchange correlation functional, which contains the exchange contribution, the correlation contribution, and whatever missing in the non-interacting picture of the kinetic energy term. Although it brings back the orbital and of course, it takes the scaling to 10 to the power 3 or 4 depending upon how you are writing it, the advantage is that it is still much less than the electron correlation method. So, this can include the electron correlation at a much less computation cost like n to the power 5 or n to the power 6. If you do CCSD band-theistic, it will be n to the power 7. Of course, you can use DLPNO, Ri cos x to reduce the scaling, maybe prefactor, but it cannot really reduce the storage and other things, whereas a DFT, although it is an n to the power 4 scaling because I bring back the orbital, it actually gives you much better answer than the Hartree-Fock. Now, question is that how good answers they give. So, let us see the examples. So, let us first see the example of LDA. So, in case of LDA, if you compare the bond energies and if you compare between experiment, the experiment is black, the Hartree-Fock is blue and LSDA is red. So, if you do the normal LSDA, you see that the actually Hartree-Fock actually overestimate the bond energy and LSD actually underestimate the bond energy. For almost every case, the Hartree-Fock is overestimating and the LSD is underestimating. So, LSDA may be slightly better than the Hartree-Fock, but you cannot get a very good conclusion out of it. Similarly, these are it is not written here, but these are for barrier heights, and here also you see the same trends. The Hartree-Fock actually, so same color coding we have used, Hartree-Fock is blue and LSDA is red and experiment is black. So, you can see that the experimental number is between Hartree-Fock and LSDA. So, Hartree-Fock actually overestimate and the LSDA actually underestimate in the case of barrier heights for these sets of compound, and in case of LSDA, in one of the cases even the magnitude is wrong. So, just doing LSDA or LDA, in one of the cases in the previous slide I have written LSDA and here I have written LDA, you may wonder why I have using two different nomenclature, because this is also interchangeably used in the literature, where just you remove the spin to write LSDA as LDA. So, just LDA approximation is not good. So, we need to go beyond LDA approximation. So, what we can do? So, what was LSDA or LDA? So, we are writing the energy as a functional of rho, and rho means, and only rho, that means only on the density. But in molecules, so that means I am only talking of density, I have no idea about the density change. But the molecule, you remember, the electron density is not spatially uniform. You remember the picture for CO, where we have shown these are the nucleus, where there is a cusp and we can get the height from the derivative of the density. That means to give the description of the system, it is not enough to just have the density, you need to know how the density is changing, because the change in the density will actually give you the magnitude of the density at different points, which will correspond to your nuclear charge, as well as it gives you idea about the position of the nuclei. So, LDA has serious limitations for energy, sometimes it gives good geometry. However, one can improve the functional by putting the information how the density is changing, like making them dependent on the extent to which the density is changing locally and the gradient of the density. So, functional that depends on both the density and the gradient of the density, they are called gradient corrected or generalized gradient corrected approximation or GGA approximation. Most of the GGA functionals are constructed with the correction being added to the term as the LDA functional. So, in case of LDA, you only have a density dependent term, whereas in case of GGA, you also have a term where the exchange correlation functional depends upon the grad of the density. You have to add correction both to the exchange as well as correlation term, because remember, exchange and correlation is parameterized differently. So, now if I do the comparison again for the same things, the bond energy, now I add a GGA functional PB is a GGA functional. Often it's written PBE because it's a PBE for the exchange and PBE for the correlation. So I am using again the same color coding. Now the PB is actually coded in green. Now you see that we were seeing that Hartree-Fock was overestimating and the LSDA was underestimating, whereas the moment I go to GGA, actually you see that they can give you very good agreement with the experiment. It is much better than Hartree-Fock itself or LSDA, and the computation cost is not so much. Actually doing GGA functionals is actually slightly cheaper than the Hartree-Fock, because the exchange term, which actually scales as n to the power 4, is Hartree-Fock exchange is not there in PBE. So you can actually factorize them if you use density fitting in n to the power 3 scaling weight. Similarly, for barrier heights also you see the same trend. Hartree-Fock overestimate, LSD underestimate, and generally the gradient corrected PV functional gives you a very good answer. So gradient correction is a good strategy to improve over the standard LSD. So these are the available LSDA and GGA functional. LSDA functionals, there is VPWN5, VPWN3, and among the pure GGA functionals, there are many of them. BLIP, PBE we have discussed. There is somewhere it must be BP86. I don't find it in the list. It said BP, but it's actually what it uses is BP86, and which is my personal favorite, not because of any other thing. It's because it's fast to doing the calculation. Now, so we have one level up from the LSDA functional. We included the gradient. We have got GGA. So the next step is that how I will go beyond GGA. Of course, the idea of getting GGA can be justified by expanding the density in a Taylor series expansion, where the density, then gradient of density, then the Hessian of density, and these terms will go on. So I have seen that including the gradient correction actually gives you improvement over the normal LSDA. So of course the next step will be to increase the second derivative of the density, that is Laplacian. So these functions where you have higher derivative included are called meta GGA because they go beyond the gradient correction, and of course you really don't write them in terms of the Hessian of the density because that is not numerically very stable. A numerically more stable approach is to include the exchange correlation functional that depends on the kinetic energy density. So that means that you write the Hessian correction as from the wave function as you will do in a Hartree-Fock calculation, but these functions are self-consistent with terms of ks orbital. So among the available meta GGA functional, it's the Fruller semi-local functional M06L, TPSS, Rep TPSS, scan functionals, and RS scan, R2 scan. They are popular meta GGA functional. So I have the gradient, I have the Hessian. So what will be the next step to include the higher derivative? There are two problems. First of all, to calculate the higher derivative of the density may not be very straightforward numerically, and we are doing integration over grids. Second thing is that including the higher derivative always does not improve over the Hessian, because it's an oscillating series. So just increasing the higher number of terms may not take it to the correct direction. So what you need to do is that you need to improve on the thing by using some other approximation, and for that we need to go what is called an adiabatic connection theorem, and that brings us to the hybrid density functional theory. So what is adiabatic connection methods? So in the case of adiabatic connection method, one take this assumption that one could control the extent of electron-electron interaction in a many electron system. Remember how we started the Kohn-Sham derivation. So we take the assumption that there is a non-interacting system which actually has the same density as the interacting system, and then we can write the kinetic energy functional in terms of this non-interacting system densities. Because I can write it exactly, because in the case of non-interacting system I can directly write the wave function as its stator determinant, and then I can get the kinetic energy term as a Hartree-Fock like formula. Now we know that although they have a same density, the non-interacting system is actually not the real system. In case of real system, in the case of molecule, there will be of course an interaction. So now I need a switch which actually connects me from the non-interacting system to the interacting system, and if I turn on the switch, it's like turn on a perturbation which takes me from the non-interacting system to the interacting system, and this perturbational handle will be called lambda, So, when my lambda is 0, it is actually a non-interacting system. When lambda is 1, it is an interacting system. Now, it is something similar to what we have discussed in terms of perturbation theory. So, that means if I want to calculate the exchange correlation functional, I can use Hellman-Feynman theorem, and I can calculate the exchange correlation functional as an integration or as an expectation value of the exchange correlation functional between this operator, and if I take the integration from 0 to 1, this will give me the exact exchange correlation functional. Now, so we have this form of exact exchange correlation functional. Now, this in the non-interacting limit, what will remain is that the only component of V is exchange, and that exchange arises due to the antisymmetry of the wave function. Remember, the correlation is the interaction between the two electron, and the when we are talking of non-interacting limit, there cannot be any correlation. So, whatever is left is in the V is actually exchange, and Slater determinant in the case of non-interacting system, we have discussed it. The Slater determinant of Kohn-Sham orbital is the exact wave function for the non-interacting Hamiltonian operator. That means, if I can calculate the expectation value here, I will get the exact exchange for the non-interacting system, and this exact exchange is actually same as the form of the Hartree-Fock exchange. Only the difference is that in case of the Hartree-Fock, they are calculated using Hartree-Fock orbital, whereas in the case of DFT, Kohn-Sham DFT, I will calculate them using Kohn-Sham orbital. So, in the non-interacting limit, the only term which will survive here is the exchange term, and that is similar to Hartree-Fock exchange. And here we will discuss how these things looks graphically. I will again go back to the slide to show you this is actually integration, and the word integration essentially means this is area under a curve. So, when I will do this integration, I will get some kind of a curve. Let us think this is my this kind of curve. So, this is my x and y axis, my y axis is energy and x axis is lambda, it is from 0 to 1, and this area under this curve, this green one from here to here. So, this is I am starting from 0, it is only Hartree-Fock exchange. So, this is my Hartree-Fock exchange, and I am turning the parameter, and it is the interaction, the exchange correlation function is increasing like this, and at the value of 1, this is the exchange correlation energy of the exact interacting system. So, this is, so now I can calculate the area. So, what I actually want to calculate is the area of this curve. So, the whole area which is inside this green curve. This is what is my exact exchange correlation functional. Now, if I take this area, so 1 into the expectation value of the exchange correlation operator between the non-interacting wave function, this will give me the area of the Hartree-Fock exchange. So, if I now want to calculate what is the total area, that means I need this area plus this area. So, now what I need to guess is only this small area. Instead of guessing the full thing, I know this part is Hartree-Fock exchange. So, this part I really need to guess. So, how I can guess this part? One easy way will be, I will calculate the whole of this rectangle, that will be 1 into the interacting expectation value of the interacting wave function. So, this will be my full area, and from this if I subtract the Hartree-Fock exchange, I will left with this upper rectangle, and this is just a fraction of this upper rectangle. So, this fraction z of the area of the above rectangle, which this can be defined like this. So, this is my expectation value of the exchange correlation operator within the interacting wave function, that is a 2 rectangle. If I subtract the lower rectangle from there, what I will be left is the upper rectangle, and a fraction of it is the term which is left above the Hartree-Fock exchange. We do not know the z, and that consider it as an empirical parameter to be optimized. Now, if I again go back to the previous slide, so what does it mean? I have this total area, from this I subtract this one, and the small area which is actually marked only in green here, this I can approximate as a some scaling parameter of the whole above rectangle area, and that scaling parameter is z. If my z is 0, that means this area is 0. If z is 1, then I will get the whole above rectangle, and if I just want to take a half of it, may not look as a bad approximation, at least as a good zeroth order approximation. In that case, I will get just half of it. So now what I am left with is that instead of guessing the whole exchange correlation functional, I have to guess only a small part of it, and that is what is done, that you approximate the whole exchange correlation functional with some choice of the DFT functional, and so area of the top rectangle is actually given by the DFT exchange correlation minus Hartree-Fock, and you multiply with the fraction that gives you the smaller green area, you add it with the Hartree-Fock exchange. Hartree-Fock actually gives you the total magnitude of the exchange correlation area. So that means we do not know the, we have discussed that we do not know the Z, so we have to consider it as an empirical parameter. So that has to optimize with respect to something, maybe experiment, maybe some high level theoretical calculation. At this point it is not important, but now at least I have an handle how to get to that area. How it is advantageous than the other approaches is that you really do not need to guess a big quantity, only guess a small fraction of it. So this is how it is written, and of course, in the actual implementation this is not written in terms of Z, but it is written in terms of another variable, that is A is equal to 1 minus Z. So with a little bit mathematical manipulation you can write the exchange correlation functional as 1 minus A DFT exchange plus 8 fraction of the Hartree-Fock exchange. Now this analysis form the basis of the adiabatic connection method, because it connects the non-interacting and full interacting states, and this actually has made the Kohn-Sham DFT theory so popular and so powerful. So on the other hand, because your everything relies on fitting this of this Z parameter, this also has made the DFT almost like a semi-empirical theory. Up to the time we were in the framework of LSDA, GGA, meta GGA, of course we are still fitting it to something, but at least we had a physical picture. So at the density, to improve upon density, I go to the gradient of the density. If my gradient of the density is not good enough, then I go to one step higher, I go to the Hessian of the density, like that I was going. But here everything finally boils down to fitting parameters and depends upon how many fitting parameters you are going to use in your calculation, and that will determine the accuracy of your final calculation. So this has made DFT almost like a semi-empirical method. I know some of the practitioners of the DFT will scoff at that, and they claim often that the DFT is an ab initio method. Remember, the Latin word ab initio means is from the first principle, and in the case of DFT your Z is obtained by fitting. So this cannot be called an ab initio method. Of course, this is my personal opinion. Now, because your exchange is actually a mixture of the DFT exchange and an Hartree-Fock exchange, these functionals are often called a hybrid functional, because it is a hybrid of it. And because you have the Hartree-Fock exchange now, your DFT functionals are no longer a local, because Hartree-Fock exchange essentially means exchange is a non-local phenomena. So if I have the Hartree-Fock exchange included, I cannot just express the densities as a like I cannot express the energy in terms of the density at a local point. So these are actually non-local functionals, these are often called hybrid function. One of the first hybrid functional was proposed by Baeke, and at 1993 he has developed a 3 parameter functional B3, and his exchange correlation functional is called B3PW91, where you start with an LSDA, you add a correction for the LSDA exchange by adding a part of the Hartree-Fock exchange, and this A is a parameter, and also you add a part of the normal DFT exchange, that is my parameter B, and for the correlation you have LSDA, and then you have a gradient correction on the top of it, and this ABC are empirical parameter. So Baeke fitted it to optimize it to 0.20, 0.72 and 0.81, and this is one of the first hybrid functionals. Whereas now we come to the most popular hybrid functional, that is B3LIP. In the case of B3LIP, the functional form is almost very similar. So it is written as same as 1 minus A LSDA plus Hartree-Fock exchange plus part of the DFT exchange, and the correlation you have writing it 1 minus C plus C times the LIP correlation. So what was my PW91 in this case? This is now added as a LIP correlation functional, and ABC has the same value as P3 PW91. This leads us to the popular exchange correlation functional that is what is called a B-tree-lip. B-tree-lip is one of the most popular functional because it gives you generally pretty good geometries and frequencies, provided you are dealing with lighter elements, carbon, hydrogen, nitrogen, this one. Of all the modern functionals, B-tree-lip has proven to be the most popular to date. It's almost like a herd mentality because everyone uses B-tree-lip, and that's why we have to also need to use B-tree-lip, whereas a good approach will be to search in the literature to see which functions other has used and which has given good agreement with some experimental results or more accurate numbers, and then from there you get up to the conclusion which function you should use. But B-tree-lip has become so popular that sometimes the DFT has become synonymous with B-tree-lip. What calculation you have done? I have done B-tree-lip. That's what the people use. But the correct word will be to use B-tree-lip, and just telling B-tree-lip is not the complete part of the story because you also need to tell the basis set, what basis set you have used. The result can be sensitive to it. These days also more and more functions are coming. Some of them are derived for physical insight, some of them has more fitting parameters, and now which function is better, there is no universal answer. It's not that the case where a wave function based method, if I use couple cluster CCSG parenthesis T in a very large basis set for everything, it will give you good answer. It's let it for energy, bond length, IR frequencies, polarizability, excited state, for every property it will converge systematically to the experimental limits if you have correct isolated gas phase experiments. Whereas in the case of DFT functional, that is not true. So, some function will give you some good result for some properties and it may not work for other properties. Whereas for that other property there may be some other functional there. So, it is almost like becomes like a zoo, and because you now have a variable in terms of how much Hartree-Fock exchange you have, by changing this Hartree-Fock exchange you can actually reproduce any number you want. But again, instead of all sorts of criticism, the hybrid DFT functions are most of the cases is the only practical thing you can do beyond energy calculation. So, couple cluster at most you can do energy calculation for any reasonable system, nothing more than that. Even for bigger system, even the energy calculation may be problematic, whereas if you want to run geometry optimization, you want to do dynamics, your DFT essentially becomes the only possible option. Adiabatic connection method incorporate both Hartree-Fock and DFT. That means I am again bringing back not only orbitals, now I am bringing Hartree-Fock like orbital because my part of the exchange is calculated like Hartree-Fock, and it has 4 index we have discussed during Hartree-Fock. So, it will having n to the power 4 scaling. So, essentially we will go back to the same Hartree-Fock kind of a scaling problem. Actually, in the case of hybrid DFT, the scaling is slightly higher than what you see in the Hartree-Fock. One important thing to note there is B-tree-lip in ORCA is not same as the B-tree-lip in Gaussian. Maybe I will show you where the difference is, but remember the B-tree-lip in Gaussian is not what is proposed in original B-tree-lip paper. It is some modification to it, whereas the B-tree-lip in ORCA follows the same parameterization which is proposed in the original paper. They generally give very similar trends. For every property, individual energy, absolute energy values might be slightly different between the two things. So, and if you want to use the B-tree-lip, the Gaussian B-tree-lip in ORCA, you have to use B-tree-lip /G. Now, again just using B-tree-lip /G may not give you a identical answer because the result between two software packages may be different due to different reasons. A big portion is that how the basis set is defined, what is the integral thresholds. So, these integrals are calculated over grids. So, up to a threshold these integrals are calculated like what you consider as 0, 10 to the power minus 14 or 10 to the power minus 18 is 0 to you. Machine precision can be a factor. How you are using the DFT grids that can be a factor. So, there are multiple factors. The energy may not match like digit by digit unless you are special careful. So, if you want to match even for the identical geometry, identical basis set, you want to match the energies digit by digit, then you have to be really careful. Of course, what always matches, when I say always, it means almost most of the time it matches is the energy differences, that will come fine. Now, among the available hybrid functionals in Gaussian, you have of course the most popular is B-tree-lip. there is PB0, BP97, and among the meta-G, so these are hybrid where the Hartree-Fock exchange is added to the GGA functional. You can also add the Hartree-Fock exchange to meta-GGA functional. You have TPSS, M06, M06-2X, the famous Tulers functionals. These are among the most popular hybrid available in the Gaussian. Now, one of the problem in the case of DFT is that Coulomb and exchange does not cancel exactly in DFT. That was an advantage because I have written the Coulomb and exchange in a separate way. Whereas in the case of Hartree-Fock, the Coulomb and exchange were exactly cancelling out for the same electron. So that means in this case of DFT, what will happen is that at long distance, the interaction, so the electron will feel an interaction with itself, and this is something which is surprising. How can an electron feel interaction with itself? So this is almost like what I like to call it, becomes like a narcissist electron. It like loves itself too much that it feels interaction with itself. It's unphysical. And in case of Hartree-Fock, it exactly will not happen because at the long distance, the Hartree-Fock and Coulomb will exactly cancel out each other. So there will be no self interaction. And this self interaction problem is not so much a problematic case in terms of valence electron, but at a long distance, if you have an ion where the electron density is spread away from the nuclear framework, if you are having Rydberg excited state where the electron excitation happens to a continuum like orbital, or charge transfer transition state where the excitation happens from one part of the molecule to the other part of the molecule, this can be a problem. And it can lead you to non-physical answers. When we will discuss about excited state, maybe we will get an example where because of the self interaction problem, it can give qualitatively wrong, not quantitative, qualitatively wrong excited states. And I have seen it multiple times that because people blindly trust this calculation, that leads to total wrong interpretation of their experimental results. So one need to be careful about this. Of course, one of the potential solution is to separate the exchange operator into a short range and long range component. The problem of this the DFT exchange, because it's not like an Hartree-Fock exchange, is actually a problem when it's in a long distance. The short range distance is not a part. So what I can do is that I can split the exchange part of the 1 by R12 interaction into a short range and a long range part, where this parameter omega controls the partitioning between these two parts. So by changing the omega, I can partition between the two parts, and the trick is to exchange different exchange functionals for short range and long range part. For short range, I will use DFT exchange as I have seen in the case of hybrid, whereas for long range, I will explicitly use an Hartree-Fock like exchange, because I know if I use an Hartree-Fock like exchange, that will exactly cancel with the Coulomb and there will be no self interaction. So this is called a range separated functional. Among the famous range separated functional is Kemp-Bithrilip. Omega B97X is actually a quite nice functional, gives you very good accurate energy for ionization potentials, and there are LC-Bilip, LC-PB, this kind of functionals, range separated hybrid functionals are available in the case of ORCA. Actually in this week's course, we have discussed too much of theory, so it's time to go back to practical and do some practical calculation.